Hello and welcome. This video covers the end of Packet 4. We covered most of Packet 4 in class, but we didn't quite finish the last couple of pages. So we're going to review where we left off and finish the rest of it. So remember that in this packet we're talking about the derivative. That's the big new concept that was introduced, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. And the derivative had three main ideas tied together. So the derivative also meant, well, the derivative for one thing, but it also means the instantaneous rate of change of a function, and it also means the slope of a tangent line. So there are those three concepts are tied together: the derivative, the instantaneous rate of change of a function, and the slope of the tangent line. So one way to help ground your understanding of the derivative is to think about position versus velocity. So note that velocity is the rate at which position changes, and here we're going to use v of t to represent velocity and s of t to represent position. So the position will just be a number, like some number. It could be negative, could be positive, could be 0. It's just some number. It's a position on a number line. The velocity would be the rate at which that position changes. So velocity in this case would be the derivative of the position function. So that prime notation there, remember, means the derivative. So this is s prime of t, which means the derivative of s with respect to t. So this also means that the velocity is the slope of the tangent line of the position function. So in our example 6, we have a robot that moves back and forth along a number line, and that the position of the robot in meters over time in seconds is given by the function s of t to the right. It's to the right on your copy of the notes. In this presentation, it's on the next slide. So the first part says graph the velocity function v of t based on the graph of s of t, the position function. So there's the graph of the position function. Just to go over it a little bit, you can see that starting at t equals 0, the position is 1. Then the position stays at 1 over the first 2 seconds until at t equals 2, the robot wakes up, starts moving to a position of 3. So at t equals 3, the position of the robot is 3. Then it, takes a nap and doesn't move at all, stays in position 3 until t equals 4, at which point the robot moves in the opposite direction, moves towards the negative direction. And it moves, looks like 4 in the negative direction, right, from a position of 3 down to a position of -1, over the 2 seconds, 2-second interval from t equals 4 to t equals 6. Then the robot turns around at t equals 6 and starts moving in the positive position direction until it ends at a position of 0. So that's how you can read the journey of the robot over the 8-second time interval. So what we're going to do is draw a picture of the velocity function. So I'll walk you through this here. What would be the velocity of the robot on the first 2-second interval? If you said 0, that's correct. So the velocity is 0 because the robot's not moving at all. So if we're graphing the velocity function, we would get just 0 for all of the values when t goes from 0 to 2. What about the velocity of the robot over the interval from 2 to 3? What would that be? If you said 2, you're correct, because the robot, so there's the 2 right there, because the robot is moving 2 meters, positive 2 meters, over that 1-second time interval. So that would be 2 meters per second. Remember, you can think about the velocity as the slope of the tangent line at any point, and if you look at the tangent lines here, like at this point right here, at about t equals 2.5, the slope of that tangent line is going to be the same as the slope of this line from t equals 2 to t equals 3. And that slope of that line is rise over run. It's 2 over 1, which is 2. And that's true of any point on this part of the line, this line right here. All right, what about the velocity of the robot from t equals 3 to t equals 4? If you said 0, that's correct, because the robot's not moving, it's staying at position 3. Or you can also think the slope of the tangent line at any point on that part of the curve is 0. Right? Horizontal line has slope 0. What about from t equals 4 to t equals 6? If you said negative 2 meters per second, that's correct. If you look at the slope of that line, you have negative 4 in the position direction divided by 2 seconds in the time direction. So rise over run, so that's negative 4 over 2, which is negative 2 for the velocity. And then lastly, from t equals 6 to t equals 8, what's the velocity? If you said a half, you're correct. So 1 over 2, which is a half meters per second. So there's the velocity graph right there. One thing I'll mention is we put all these little open circles at the beginning and ending of each of these little line segments because we don't really know exactly what the velocity is at these t values. At t equals 2, the velocity suddenly changes from 0 to 2. And so because of that jump in the velocity, there's not really a particular value we can say that we have at t equals 2. We'll look a little bit more into this, how at a corner the graph doesn't have a derivative, or in other words, the derivative does not exist, in some upcoming slides. But for now, just for these kind of problems, you would put little open circles because, again, you don't know what the velocity is exactly at those periods. Is it 0? Is it 2? Kind of hard to say. All right, so moving on. Part B says find the first derivative of the position function at t equals 1. All right, well, the first derivative of the position function is the velocity function. Velocity is the first derivative of the position function. So we just have to find the velocity at t equals 1. So if we look over here to our velocity function and we read off the value of the velocity at that t value, you should get 0 meters per second. 0 meters per second. The y value there is 0 of the velocity function. What about s prime of 5? What would that be? If you said negative 2 meters per second, that's correct. Make sure you put the units on these problems here, because we have units we have units. So here at t equals 5, you can see that the velocity is negative 2, just from reading off the graph. What about s prime of 6? If you said does not exist or undefined, that's correct. Right here at t equals 6, there isn't really a velocity to speak of. It's not exactly negative 2, but it's not exactly a half either. It's kind of unknown. It's undefined. You can write undefined here if you want, or it does not exist, because the derivative is both a function, which can be undefined, and it's a limit, which cannot exist. So v of 7 then? Well, just reading off v of 7, that's a half meters per second. All right, so that's example 6. Let's try comparing a more arbitrary function and one that's smoother, so it doesn't suddenly change direction like we did in the previous example. So here's a function, f of x. You can see it's not jaggedy, it has all these smooth curves, so it could be like a polynomial. And down below it, we have f prime of x. There's the prime, which says that this is the derivative of f at x. So these values of f prime of x should be the slope of the tangent line of f of x. So if you look at the tangent line at any given place on f of x, the slope of that line should be what f prime of x is. Now there's some key places that I want to point out. One is at the top of f of x right here, at the top of this peak right here, round t equals 3, what is the slope of the tangent line? If you said 0, that's correct. If you take a tangent line right there, so a tangent line just goes in the same direction as the curve at that point, then the slope of that tangent line is 0. The slope of a horizontal line is 0. And if you look down at f prime of x, you get a value of 0 at t equals 3, or close to t equals 3 at least. So that's going to happen anytime you have a horizontal tangent line of your function. The slope of that horizontal tangent line will be 0, and that'll correspond with f prime of x being 0. So the next place that we get a horizontal tangent line is somewhere like right around here, close to t equals 6. There's going to be a horizontal tangent line. And if you look down, there f prime is 0. And then we have one more place, which is right before t equals 8, somewhere around t equals 7.7 or something like that. Now in between these key places are, we can see that the derivative is giving you values of the slope of the tangent line. For example, on the interval from 2 to 3, if you pick a point and you look at the tangent line, that's going to have a big positive slope. And here we're seeing that the values of f prime of x are big positive numbers. If you pick a point from t equals 3 to t equals 6, and you draw a tangent line, well, that's going to have a negative slope. And if you look down at f prime of x, which is all lined up, you see negative values for f prime of x. So these are the negative slopes that we're getting for the tangent lines. So, and then also from t equals 6 to t equals, I guess whatever that is, 7.75, if we pick a point, we get a positive slope, so we're going to have positive values of f prime of x. They're kind of peaking right here when the slope gets the steepest, and then it gets less and less steep after that. And so you can draw, if you're given the graph of f of x, you can draw a rough sketch of f prime of x. All right, well, I'm going to stop right here and continue this on in the next video. Thank you for watching.